Hello, I'm Yuri from the University of Wisconsin-Madison. In this video, I'm going to present our work, Understanding Uncertainty Maps in Vision with Statistical Testing. Hope you enjoy it. Quantitative description of uncertainties of the predictions are needed in a broad spectrum of applications in vision and machine learning. For example, it can be used for calibration of the model in problems like generation, depth estimation, and segmentation. Among current deep learning methods, there exist several different ways to generate uncertainty mask. For instance, Bayesian neural network, where all weights considered to be random, variational autoencoder, where the latent representation is random, or even Monte Carlo dropout, which approximates posterior distribution of deep Gaussian process. However, while there exist different methods to generate uncertainty, one thing is not clear. Which uncertainties are significant? Consider two different problems, generation and segmentation, and their corresponding uncertainties. Unfortunately, the scale of generated uncertainties varies a lot, which makes it very subjective to understand which uncertainties are really significant. Now, consider only the generation problem with corresponding uncertainty mask. Deriving a scientifically valid conclusion for the image based on pixel-wise statistical tests will require conducting many tests equal to the number of pixels. For example, an image of size 28 by 28 leads to 784 tests. For a common 0.05 critical value, which corresponds to probability of type 1 error, we expect to select about 40 pixels as significant purely by chance, which is number of false positives. The issue escalates for higher resolution images, say 3D medical images. To control a family-wise error rate and avoiding inflating the number of false positives, a multiple testing correction like a Bonferroni is used. However, for high-resolution images common in vision, this tends to overcorrect, making none of the testing significant, making the analysis less meaningful. Another method common in deep learning is to select the specific threshold based on quantile. However, it generates very different significant regions, which makes it hard to understand which threshold to use, especially if you desire theoretical properties like a control over type 1 error. Note that generated uncertainty mask can be considered as a general random field. Consider a theoretical random field with nice properties. According to random field theory, we can derive the significant region without assuming independence of the pixels, which is important in vision problem, and preserving family-wise error. However, it works for very special random field, like isotropic Gaussian, while uncertainty mask from neural network is definitely not isotropic Gaussian random field. Thus, theory of random field cannot be applied directly. Then what to do? A great founding was the statement of the John Taylor in one of his papers that the domain of the random field could be warped or deformed by a one-to-one smooth transform without fundamentally changing the nature of the problem. What does it mean for us? In our paper, we showed that in theory, we can warp observed random field to Gaussian random field. Apply a random field theory to detect significant region on Gaussian random field, and then apply reverse warping to get a significant region on the source domain. Such approach allows us to derive significant region assuming dependency on pixels and controlling family-wise error. Main problem is how can we learn such one-to-one mapping? To learn mapping or warping, we propose a new method, warping neural ODE. The idea is to model the warping phi as a member of a Lie group parameterized by differential equation, where the force V is parameterized by a neural network. The main feature of Lie group is that reverse warping can be computed by running differential equation in reverse. Once model is trained, it allows us to define warp at any time step, and thus we can define forward and reverse warping. We show our approach works with different ways to generate uncertainty in different setups, for different architectures of neural network, and for a wide variety of datasets. Thank you and hope you enjoy the paper.